Welcome and a lovely evening, everybody. Thanks for joining the Elastic Meetup today. We have two speakers today. We have my dear colleague Girish, who will talk about KNN vector scoring. And we have Philip from Elastic talking about security.
Yes, welcome everyone. Yeah, my name is Girish. I work in the search department, mostly also in the full text search team. Yeah, so we did some experiments with vector search and how we want to utilize to enrich our customer experience. Yeah, so let me get started. I will give you some, yeah, the agenda, some introduction and background, what I will focus on, what I will not focus on, and the macro benchmark setup. So that is how we ran our experiments. We'll give you the overview. So that's the high-level overview, and then there's the experiment setup, more in-depth details of how the setup was built. Yeah, and then some experiment results that we have so far. Yeah, and then the conclusion and Q&A at the end. So yeah, so if you have any questions also, feel free to ask me or at the end. So it's a small introduction. Also, I want to take the opportunity to say what I will focus on and what I will not focus on. So we already had a deep learning-based neural network model, and already since 2019. Yeah. So this one, I'm not the expert, so I just want to give a quick overview in case somebody is wondering where does this vector come from. So this is like the very basic vector model that you can think of, or actually we built to first start experimenting even with deep learning. So even before deep learning, this was the baseline model. So basically the lookup is basically encoded. So you encode your queries into vectors, 1 or 0s, and also your product IDs, experiments into 100 dimensions. And then, yeah, so you have a vector of 100 dimensions, and then you have your dot product, cosine similarity and other kinds of similarity, and you get a score. So what the score is saying is how far or how near is my product to my query. So yeah, so we have done a lot of improvements since then. In fact, recently we also upgraded the model to 200 dimensions, added a lot of other features using like deep learning, PyTorch, and other things. Yeah, so that will not be the focus of this talk because I think my team, my colleagues are the experts and probably will talk about this later in the year. And so what I want to focus on is the dot product, right? So we have queries and we have a lot of products. How do you calculate the scores, and how do we do it with Elasticsearch? So what does Elasticsearch provide, and yeah, and what use cases basically we want to do? Yeah. Also, like some background about the model also, that it works. So these were some no-hit queries that were enriched by the model. So, yeah. So what we do is we still have the traditional classical search pipeline, and we use our the vector search or the deep learning model to kind of enrich or supplement the traditional results. So what we have here is like, yeah, more vague queries or queries which are not properly represented in product attributes. So the model can learn these attributes, and then we have some valid results. So the first row is, yeah, it's in German, so probably I can translate to my best of knowledge. So yeah, the first one is, yeah, Abendkleid Tattoo-Spitze. Yeah, so it's basically like, yeah, for evening dress. I think what Tattoo-Spitze is, I think in your top there is like a tattoo pattern or something like this. So yeah, so basically this was not properly also captured in the product data. So how do you represent this, or was not done? But our model was able to learn. And the second row is for like a top form fitting or very shape fitting dress top. And the last one is yeah, like a blouse in Senf. Senf is the mustard color, the yellow mustard color. So yeah. So this is just an example to show what our model can do so far. But this is an older model that we have. Yeah. So going back, so we'll focus on Elasticsearch. We have some query embeddings, we have some product embeddings, and then how do we calculate the similarity vector and then generate a result set which is scored by the vector dot product. Okay, so in the second section, I want to go over the macro benchmark setup. So it's still on a high level overview on why we chose this macro benchmark and what it actually means for us. So how did we define this, or what is our definition for this? Yeah, so basically the word macro is that it's large, right? So we have one or two systems or more systems in the benchmark. So the benchmark, if you see in a normal day-to-day like software engineering, you're benchmarking like a function or a module or a package or something. But we kind of extended or blew this up to have multiple systems. So yeah, so that's the macro word here. So yeah, why did we want to do the benchmark? So there are multiple ways that you can test the value that you're adding to your product, right, to your customer experience. So you already use configurations, feature flags, A/B testing and things. Yeah, but for this one, we chose the benchmark. Basically, yeah, so some background on some such metrics performance at Zalando. So going one by one, so we have around like 500 searches at the peak on a weekend or Sunday night. Otherwise, it's around at least 300. So this is only the full text search and not the catalog search. And then, yeah, product choices. So depending on the market, we have anywhere from between 300,000 to more than 1 million products. And yeah, so these are separated into different indices. So we have multiple of them. Yeah, languages. So we also expanded into Eastern Europe this year and last year also. So I think we have a total of 21 languages. Okay, just a second. Maybe I will allow. Yeah. Yes, and also the efficiency or the impact of our neural search model was, or the usage now is 20% of all full text search traffic. So it's enrichment. So the traditional model or pipeline still runs, and then 20% of those has some input or supplement from our neural search. And the first model that we also properly A/B tested resulted in a 2.5% revenue uplift. Yeah, since then we have also made smaller improvements, so it's definitely been improved beyond that. And yeah, the number of Elasticsearch nodes, so we have between 100 to 160 as an average number during the normal operating times. Yeah, so coming back to the benchmark, yeah, so that's the workhorse. So Elasticsearch is our workhorse and core infrastructure. And we have like two different types of workhorses, basically. I will go in detail later. So if we add additional features, how would it perform, right? So, will it be stable, right? So, and also with this benchmark, the macro with involving multiple systems is that we want it to be as close to the user experience as possible, right? So every feature that is part of the critical flow should be included and should be well tested and see how it works out. Yeah. And also with the benchmark, when we upgrade Elasticsearch or any other system, we can put it into the benchmark first and then verify if the performance and stability is as we expected it to work. So, yeah. So again, some high-level overview of how we achieve this. So we use Kubernetes. So we can build a sandbox namespace, basically, a throwaway namespace. And then we have three main components, like the Locust, which is our load testing or the one that is producing the load for the benchmark. And then we have our backend service, which has a lot of business logic that be there. So personalization, ranking, sorting, A/B tests, and all those things. So everything that is in production is reconfigured here and to reproduce as close as what we use in production. And then, of course, Elasticsearch. Yeah, on the right-hand side, just for some offline data construction. So we have request logs to our backend service saved in S3. So we took a defined time frame and then used Databricks notebooks and then converted those request logs to use vector search, basically. Yeah, and the sandbox also kind of like enables us to quickly test any changes that we want, either in Elasticsearch or in our backend service, any configuration that we want to try out, debugging, and those things. So I think that was why we wanted to have a more deeper understanding before we started introducing it into a production environment. Yeah, so in the third section, I will go deeper into the setup. So what do we have so far? So the first step, also one of the important features that we wanted is to make it automated. So we wanted to build the sandbox on demand. You push a button and then all the infrastructure should come up automatically without much effort. So in this, because it's like a throwaway sandbox environment, you can deploy our backend service, Elasticsearch, and then we populate the data fresh into the Elasticsearch cluster. So it's a completely new environment. What we have, and you just click of a button, all your components should be there. So the second step is the Locust. So after once your data is there and you're ready to execute the benchmark, you can deploy the Locust. So the Locust execute this queries, and then you have like a bunch of parameters that we can measure, basically like CPU, our latencies at Elasticsearch, our backend service, memory, and things, and even So once the Locust test runs, we save it to S3 again. So it's the cloud data going into the cloud. And then we can also monitor in Grafana. So we have in our own sandbox environment, you can monitor our SLOs. SLOs in the sense the latency, RPS, CPU, and memory. So this is what we can monitor. So once this testing phase runs, so this is just a sneak peek of how the result looks like, with the RPS and the request latency. So if you look at the right-hand side, the latency is P95, P99, and P999. So in all of our experiments, we did find that it was pretty stable. So it's just a sneak peek from an old benchmark that we ran. And just to give you an idea of that there's no like a sawtooth pattern or spikiness in the benchmark. So it has been, so this is what you can see in our monitoring dashboards. So once this is done, it's about tearing down our infrastructure. So either you can delete the namespace and everything goes away, or in our sandbox environment, we actually have you can set a TTL on your resources. Say it expires after like 1 hour to 2 hours, and then it automatically gets cleaned up. one of the nice features. Yes. Yeah, so said what is not currently available or not yet implemented is, yeah, so as I said, we populate the data once at the beginning before running the Locust load test. And during the test, there is no write traffic. This can be an important performance metric that can affect your query performance with vector search or normal search also. Yeah, search quality. I said the models, we are still trying to improve them. So yeah, we still don't have a way to measure the search quality, how the model and the similarity score perform, basically. Yeah, so even more metrics, like our application metrics itself, there are other timers that we have to measure for our business logic functions, and of course, Elasticsearch metrics, a lot of metrics like threads, memory, JVM. And the Locust metrics can be saved to S3, but we don't have a way to kind of compare them automatically. So this is useful because if you upgrade your Elasticsearch or if you add a different model, then it's useful to compare between like an older benchmark and a newer benchmark. This is an idea that we have. Okay. So it's time for some more details on the experiment setup. So again, going from the top, the Locust. So the Locust has a master node, a coordinating node, and then we have 4 workers. So for our benchmark, we had set it to like, I think maximum 20 users per worker. And yeah, so there's also a feature called a load test shape in Locust. So you can define what kind of user profile that needs to be run on your service. So I will explain later. So what we had is a ramp up. So basically this is a completely new environment, no request from external or internal. So we ramp up for 2 minutes with just like some 10 users. And then we have stage 1. I will explain later what does stage 1 and stage 2 mean. Yeah, and then stage 2. So each will run for 5 minutes with 20 users each. With the normal spawn rate of 5 users. So this is just something that we started with initially. And our backend service, nothing much. Yeah, it's written in Scala and Akka HTTP. So the main thing here is the configurations and all the settings have to be the same as the production, and all the other internal dependency, except for one external dependency, everything was mocked or set to the production values. We started with 3 replicas, and then it could scale if the load was higher. So we made some minimal changes here, so we don't have to go through the normal production review and all those things. So quick changes to incorporate the 2 algorithms, so converting the queries into either exact KNN or the approximate nearest neighbors queries. So some more details on the actual Elasticsearch setup. So at the beginning of the year, I think when we had this thinking about running this benchmark, we are currently running on 7.7 in production, and version 8 was released with the approximate nearest neighbors. So we thought, okay, why not benchmark this and see if there were any significant improvements there. And then, as I said before, like 2 types of workhorses. So we have the C5 D.9x large, which is our the ultra performance. Ultra is the short name that we use. So with mostly like max, not max, but a lot of CPUs, and then also the high performance, which is the M5D.4x large EC2 instance type for other, So basically, we have these 2 hardware set up because of the different profiles that we have in Zalando. So we have a lot of markets where we have low traffic and some markets where we have high traffic. So the read and write load might be higher. So we group them in the ultra EC2 instances, and the other ones which have like low traffic or medium kind of traffic, group them in the high EC2 instance type. Yeah, so because we have these two setups, so it's important whether to check if it works consistently in both type of instance types. Yeah, so for the benchmark itself, we just had like 6 data nodes, one index with 6 shards and 2 replicas. And the number of products that we had is, at the benchmark that I used was almost 1.4 million products. And then the embedding size. So use the dense vector type for both 100 dimension and 200 dimensions. Algorithms. So as I said, the exact KNN was already used in 7, I think, and the approximate KNN, approximate nearest neighbor in version 8. So in what we used in 8.1, there was no filtering support, basically. So your top K neighbors was basically for the fetched on the 1.4 million products that we had in the index. Yeah, so I do not have much time. So for those of you who are not aware of what this exact KNN does, it's basically takes your normal query to Elasticsearch and then wraps up in a script score. What does the script score? In there, it's just basically substituting the cosine vector calculation to calculate your actual similarity score. So we have 100 dimensions, so our actual query would be too large to be put on the slide. So I took it from the documentation. So take your query, wrap it into a script score. The score is basically a dot product of your query and your product vector. Yeah, so the approximate nearest neighbor is a little bit different. So if you're aware, it uses the newer algorithm. I forget the name right now. So it's a different API. So it's called the KNN, the approximate nearest neighbor API. So it's just purely retrieval based on your dot product between the query vector and your product vectors. And it's the newer improved, so it does a trade-off between speed and accuracy. Since we had not implemented this in our backend, so we decided to have Locust, get the top K candidates for our query vector, and then send it to our normal backend, because our backend still has a lot of business logic for ranking, sorting, those kinds of things. Okay, search queries. So how did we get our search queries? So as I said, we have request logs in S3. So it was actually like our 100K full text search request logs collected over 1 week. So they have everything with paging, information, filtering on the same full text search query. So like the whole user journey was there. So the stage 1. So we took the query and then we converted it to a script score query for the exact KNN. So it was stage 1. And then stage 2 is we had the same like the user journey and the query. So, and then what we did was we just filtered on the top categories of what the script or the query was executed on. So either it was on the like the whole catalog, if you're browsing on the unisex, or if it was on men or women or kids. So these were our top categories. So this was important because to know your performance when you have no hits, so you are basically looking at your whole catalog or apply some kind of filter to restrict your candidates, and then you get your top candidates. So that's what we also wanted to measure. Yes, so some experiment results right now. So there are different ways to represent this. So what I did was I split them first by the algorithm, so exact KNN, and then with your 100-dimension embedding. So yeah, so below you can see on the on the horizontal axis, the Elasticsearch version 7.17, comma high is the short name for our EC2 instance type. Yeah, and then the red bar RPS is the mean RPS. So decided to just use the mean RPS because we didn't notice any like a sawtooth or spiky patterns because we benchmark ran queries over the whole catalog and also with the filter and those kinds of things. So we didn't notice that. So here, basically what you have to watch out is that look for is the RPS means that it's your throughput because we are using Locust. So Locust, what it does is, it does not have a target RPS, but rather more looks towards the maximum load or the users that add load to your system. So as soon as a user completes its search request, the next user will start. So it's kind of like a measure of throughput. So how many search requests can you basically execute in the setup? So the higher the throughput is good and lower the latency is good. So that's what we are looking for. Yeah, so in the, starting from the left-hand side, if you see the first one in 7.7 and with the high EC2 instance type, which is like 16 CPUs. Yeah, so the throughput is slightly lower and the latency is about 100 milliseconds. But actually, if you look on the third graph or the third set of results with 8.1 and the high EC2 instance, throughput is actually comparable to the other versions, to the Ultra with 36 CPUs. So this means that Elastic did some improvements, so which gives us a good reason to switch to 8.1 or higher for us. So with 100 dimension and for our EC2 types, so it's pretty good. So latency is around 75 milliseconds, and throughput is also above 700. So this gives us a good indication that both of them can be used up to a certain extent. So no major performance degradation or unexpected behavior, basically.
A question on high versus ultra in 8.1, right? There's no additional latency, and also the throughput is basically the same.
Mm-hmm. Yeah.
Does that mean adding more CPU cores for 8.1, at least for our setup, didn't help?
Yes. So basically, I think with exhaustive search, there's some ceiling that you hit. Adding more CPUs will not help anymore. Yeah, so the next one. So the exact KNN with 200 dimension embedding. So with 200 dimension, how will it perform? So the first one with 7.5, 7.7 version and the high instance type, you can see that the throughput is low, the high latency. So this indicates like very high performance degradation. So when you choose your model, so I have to be careful if it's using for a specific use case or not, or if you really want to use this 200 dimensions, or if the value that you're adding with 200 dimensions is really worth the cost. Yeah, but then going further than that, I think with the Ultra and the 8.1 setup, it's pretty good. Although with the high instance type, I think throughput is a little bit lower at the 200 dimensions. With the Ultra, it's slightly better. I think the latency and throughput is slightly higher. So so some improvements are there, which can, with more CPU, you'll definitely get benefits. So next is the approximate nearest neighbors with 100 dimensions. So what we have here is actually 3 metrics that you see here. So again, the red one is actually the backend RPS, so which is the same as before. And then we have the blue color is the Elasticsearch latency. So I think here we decided to measure it because there's an additional, the Approximate NN API, which fetches the top K candidates. Yeah, so we also want to measure and visualize if there's any instability or like a sawtooth pattern or spiky behavior where in some use cases it's not responding well. Yeah, so I don't know if you can see all the numbers properly. So maybe I'll come here. So what we have here is I've paired the 200 dimensions here together. So 200 means the number of candidates that we fetched from the Approximate Nearest Neighbor API. So we did, so there was 200, 500, and 1,000 candidates. So this is, we're still trying to figure out how to use this. So as we said, our neural search, we're still trying to enrich our traditional search pipeline. So what is this number is, I think we still have to figure out, but we started at 200 because there was no filtering at that point. So you could not filter to like your men or women or not even like a brand or something like this. So this was, so that's why I started with 200, at least this will give like 2 pages of search results for us. Yeah, and then again, like the in pairs, so 200 comma high and 200 comma ultra. So for every 200, so it's pairwise you can watch. So for the 100 dimension, comparing between the high and ultra for 200 candidates. So yeah, I mean, with more CPU, this definitely performs better. So 355 RPS, like the mean RPS versus 193 for for the high instance type. So even though the latency is a little bit higher, but the throughput is like only half of what you see. Yeah, here the backend latency is mostly fetching the product IDs. So it's also adding some custom ranking functions which satisfy our requirements. So it's around 40 to 50 milliseconds. I think the first one with like 74 milliseconds. Yeah, I think we just need to double check and rerun it again and see if it's consistent. So going next with getting the top 500 candidates, it's like the similar pattern that you can see. You have like about 329 RPS and versus 187 for the high instance type. So higher latency and higher throughput. So depends on your use case. So again, going to 1,000 candidates. So degrades in both models a little bit, but I think the degradation on the high instance type is a little bit higher. Or it just doesn't seem like it degrades so much because throughput is still 249, but the latency goes up because I think what Elasticsearch is trying to do some trade-off with your speed and getting your top nearest 1,000 candidates. And then we have the last one with Approximate Nearest Neighbors with 200 dimensions. So again, it's the same pairing with 200 top 200 candidates with high and ultra. And then we have the same one with 500 and 1,000. So for the fetching 200 candidates is performant, but anything above, going 500 is okay. I guess it depends on what are your requirements and SLOs. And then, fetching 1,000 candidates, drops even further higher, and the latency goes up. So the main conclusion that we have so far is, depending on your use case, whether you want to exhaustively rank or calculate the similarity score for all your products, or you want to use the approximate KNN to get only the top K candidates and then use it as your enrichments. So we have these numbers, and you will decide how to implement this for our customer experience. Yeah, so I think this concludes my talk. So if you have any questions, I can answer them. Thank you.
Check, check. Okay. Any questions to Girish?
Did I read the numbers right that exact nearest neighbor search was faster than the approximate nearest neighbor search, which I find quite surprising? Or is this something I misunderstood? So when we have here the latency, it's like 100 milliseconds, and when you go back to the exact, it was way below 100 milliseconds.
Yes. Wait. So are you referring to this one, the 200
exactly.
dimensions? Yeah, 200 dimensions and to the 8.1, you mean?
Exactly. So this is faster than the approximate.
In the ultra. So in 200 dimensions, not really. So it's pretty high, right? So it depends on with the approximate NN. It's not like a direct apples to apples comparison, right? Because with the exhaustive KNN, you are ranking or calculating the scores for all products. But with approximate KNN, there are two steps, right? So if you're looking at Elasticsearch latency, you get the top K candidates, and for us, we have to go pass it through our additional ranking criteria functions. So it's a two-step process. Yeah. So if you look at the ultra for 200 dimensions, like here, the second group of metrics, here it's still like it's only like 300 RPS is the throughput. Yeah, so the latency is a little bit low, but the throughput is still lower at the backend entry point. Yeah.
So if you would include in the script scoring score also the original BM25 score, potentially the script scoring is at least for your data size faster than the approximate nearest neighbor, since you need the re-ranking step.
Yeah. So it depends on which model you're scoring. If your model is already capturing the similarity score, like the BM25, then you can use the exact KNN. Otherwise, you might have to try it with the approximate nearest neighbors.
Yeah, I'm coming more from the infrastructure point of view. And when you look into Elastic infrastructure, you try to understand always number of indices, number of replicas. Mm-hmm. So how do you see the impact in this dimension, in the initial sizing dimension for the Elastic cluster? And how's the impact in the results? When you, for example, increase the number of indices or increasing or decreasing the number of replicas?
Yeah, so the thing with the exact KNN, like we saw, you will hit at some point a threshold of how many CPUs. Adding more CPUs will not be beneficial for you. So with the 8.1 Ultra, so as I understand the replicas, so with the exact KNN, it still works as your normal search. So the more replicas, so then you can have more read traffic. But it's already mentioned with the exact KNN, it's your performance increases linearly with the number of vectors or the dimension of your vector. Right. So even if you add more replicas, like the math library that calculates based on your CPU, right? So that's where you will hit the limitation, from my understanding. Yeah. So it's again experimentation based on your usage. So what kind of queries that you have, what kind of analysis that you have. Yeah. Apart from this, just focusing on the dot product. Yeah. So this will definitely be restricted to your CPUs.
Maybe related to this, have we experimented with different shard setups? Because from my understanding, we could also benefit from more parallelism if we shard more. I mean,
yeah, I think we only did it with like 6 shards. So increasing the shards also will work if you have primary read traffic. Yeah.
any other question?
Thanks, Girish. I was wondering how the results look like from like products perspective. Did you pick them? Like, do you have some examples? Because I think what you showed as examples for the previous implementation, right? So for this one, do you have some examples?
No, not yet. The thing is that the model is not tuned properly to what we want to achieve. So what we have is like, so these embeddings were from the older model that we have. So, and the 100K search results, what we have, or the search logs, so they already perform well. So they are the head of the search request pattern, right? So I think where what we want to do is like enrichment for when there's no hits or we don't have enough products. So I think in this benchmark, we did not have that within the 100K. So it was hard to find. So I tried because of the short notice. I couldn't find a good example for now.
All right, one more question maybe. Maybe I could check Slido for a second, see if there's a question. Otherwise, if any one of you still has a question while I'm typing.
So in terms of the kind of like the architecture within do you do the maybe it'll come the recording this way. Yeah, so in your Elasticsearch cluster, is it arranged in such a way that you have some kind of like a client-only node, which is doing the after, so you have multiple shards being served by multiple data nodes. They will do the, I guess, the initial, cosine similarity, but then once you have a certain number of candidates coming up from the various shards, you have to maybe, are you doing any kind of, like a gather phase after the scatter?
No, we haven't looked into it yet. So we just use data nodes for now. So yeah, so there is no like the scatter and gather phase if the gather phase is on a dedicated node, which can improve performance maybe. We have not done that yet.